Hello all, myself Shiva and I'm from Qualcomm India Private Limited. Today I'm going to walk you through the progress we made with large language models on Adreno GPUs using OpenCL backend. On the agenda today I have a little intro on what is generative AI and large language models and various typical challenges that the edge devices will have while enabling these kind of models. Then I'll be talking about some baseline reference that we have taken for enabling these models on Adreno GPUs and followed by I'll talk about some performance improvements we have made. And finally, I'll give you some details on what is it that we are working on in near future with respect to enabling more LLM architectures. And also, I'll give you some details of how someone can try out our enhancements by using the open source contributions we made into the communities. Many of you probably know about generative AI with popular terminologies like ChatGPT, prompt engineering, and all these buzzwords which is going all around. AI is significantly evolving more than a decade. While we talk about generative AI in recent years, there is a question obviously that what is the kind of AI that we are using all the time. I would probably call it as discriminative AI. As what it used to do is it used to learn the boundaries in the given data. Some of the use cases of discriminative AI are like classification, object detection, segmentation, and wide variety of image quality enhancement models. So in all these models, they try to tell you what is already been there. For example, if you show an image of a cat, it will tell you a cat. As a human, we know what it is, but yeah, this model has an intelligence to clearly tell what is already been there. There's nothing that they're telling you something which we don't know in all those models. Alternatively, the generative AI models is more focused on vending new data which the human never seen before. So these models are being built with the aim of understanding the underlying probability distribution, and then with sufficient amount of training with different data, they technically can synthesize new data, which in a meaningful way, basically. So, and in these kind of a models, we see in a wide variety of networks based on GANs and variational autoencoders and transformers. We now have generative AI models that can emit text, image, video, speech, and even there are models which can do a combination of all these. And today we're going to focus about large language models, which are primarily the models that can synthesize text data for us. So these models are in general trained with volumes of data, probably from the data from Wikipedia, GitHub, and a bunch of archives and various different sources where you get truckloads of data. The applications in these places are aggressively evolving, and we now have various variants of these large language model that can do answering, article writing, and language translations, and they can even do a very good programming code out of given a requirement. Coming to some of the challenges that edge devices may face with these kind of models on the device. As the name says, generative models, these models need significant amount of knowledge in terms of parameters. The parameter size for these models will vary from uh, we have like 1.5 and 3 billion, and then they might go all the way up to 180 and 200 billion parameters. A simple 7 billion model with a simple 7 billion parameter model technically will have 12 GB of trained parameters on the target. So the challenge starts here by from how do we place such a massive parameters on the edge devices with a limited RAM capacity. So DDR throughput is also a key out here for because every inference that we do with these models involves all these parameters to be consumed by the model. While the response that is coming out of these models is a DDR bound, the prompt that we give for these models is primarily driven by is bounded by the ALUs that we have on the target device. The larger user prompt is going to be there, the more compute power it requires to process the user prompt into a kind of context information. Basically, the large language models here are pressing the limits of both memory and compute power on the edge devices. Large language model has brought new set of operators into the DNA networks, like there is attention layers, which does a lot of, which are pretty computationally complex compared to the kind of layers we used to see in conv nets and all that. And large language models, we need to do a lot of optimizations. For example, the softmax is not a new layer which has been there for a long time, but the amount of computation power softmax used to use in the earlier layers is like pretty tiny compared to the complex layers like convolution in those days. But now the large language models, they use grouped softmax with a very big softmax vector length, which is slightly popping up as a significant compute intensive layer in the overall profiling. And LLMs has introduced attention layers and variations of attention layers which need edge optimizations. And similarly, these LLMs will have a context, because it's not like one time you make an inference call and then you get an output and then we are done with that. The sequence of inference calls will keep a context on it, because there is a correlation between your previous inference versus the current inference. So this requires a lot of context to be maintained on the device, and it's going to be a challenge on the edge devices, because you need to keep track of these dynamically growing memory objects on the edge devices. These are the few high-level challenges that we have with LLMs on edge device, and while implementation, yeah, there are much more challenges than this. Coming to the baseline reference, what we have taken when we started all these effort some time back, we took the Llama models from Meta. Basically, Llama is a collection of language models from Meta. Meta has released multiple versions of these. The very first model that came in 2023 Feb with the name of Llama, and then we have a further enhanced version of it at mid of 2023. And the parameters for these models are ranging from 7 billion all the way up to 70 billion. And Llama 13B model used to outperform ChatGPT 3 in most of the benchmarks. So this shows the ChatGPT 3 requires about 175 billion parameters, but 13 billion parameters of Llama model was able to significantly outperform the ChatGPT 3 model out here. And yeah, these Llama bunch of models are pretty competitive when compared to the other guys. And when you wanted to look at the kind of competition we had with respect to this model, there are a bunch of open source models that are tightly competing with Llama, like MPT, and then Mistral, yeah, is surfacing on the top in recent times. And at the same time, there is quite a few private LLMs from Palm and Chinchilla and ChatGPTs and all these players in the market. Coming to the framework that we have used for enabling these Llama models from Meta, uh, we have taken the baseline reference from MLC.ai. Those who don't know the MLC.ai, it's a machine learning compilation community which is which under the hood utilizes the TVM runtime. And the main aim of this MLC.ai community is to quickly transform and optimize these generative AI and the upcoming AI workloads from a development farm to a deployment farm. So yeah, this community right now offers multiple sub projects for one for LLM and then web LLM as well as a stable diffusion model too. So coming to what is this deployment farm and development farm, when the researchers are making these are enabling developing these models, they primarily will be playing at the high level where you have probably a PyTorch or a TensorFlow kind of a framework, and then that the and you they do lots of optimization training, and then finally they have a very well tuned model that can give you impressive results out of it. But when you look at the deployment environment, right? So deployment environment, the same models can go and sit on a cloud, and then they can even sit on a mobile device, and then which has a balanced power and the memory. And then when it comes to edge devices, it's pretty constrained environment where you have limited amount of resources, and we'll be having we sometimes need to pay attention to the power also, with the perf per watt is going to be pretty significant on the edge devices. So the challenge out here is the target environments are pretty diversified in terms of hardwares and the environments and the capabilities of the targets and things like that. And for getting best results in all these various different environments, we need a kind of a tailored solutions. The source is going to be the same model, but the environment that is going to run is entirely different and diversified. And we need the framework that can scale over a period of time. Today we tried with Llama, and tomorrow there might be some other architecture, and then the things are evolving exponentially on the generative AI domain, and then we need the frameworks that can catch up with that innovation and then make these solutions available on the edge devices. And what essentially MLC does that under the hood is MLC will has defined that high level workflow which can consume these models from the developers or the researchers, and it quickly converts that into a kind of a framework invariant form, which we call it as IR modules in TVM terminology. And there is a quite a good amount of transforms it will go through, and these transforms basically convert that in two stages. One stage is probably the target or hardware independent transforms like the quantizations and these kind of a things. And at the second stage, they try to tailor these or optimize these this model with respect to the target. Yeah, looking at what is a kind of a parallel concurrency I have it on the target device, and the amount of memory we have, and then how do we make sure these layers are efficient out there. And finally, it does generate a optimized version of target code for you, which anybody can take it and then deploy it on the device. So the MLC has got all that things that are required to accommodate these generative AI models. Yeah. So the trick is going to be when I said we have taken a 7 billion llama model for our experiments. As I said, 7 billion llama model realizes totally about 12 GB of parameters on the target device. So if you look at these Android devices right now into market, we are like 12, 16, or maximum 24 GB of RAM. So the challenge is like, I mean, how do we place this 12 GB of RAM on the parameters? If we place 12 GB, when we start using 12 GB of RAM on the device, so how about the RAM for the remaining applications on the device? And do we have enough bandwidth to use this 12 GB parameters from DDR all the way to the Adreno GPU core? So these are the questions that will come out. So MLC has got in this quantization mechanism where we try to quantize all these parameters into a 4-bit representation, which drastically brings down the overall size to one-fourth of the original size. So how it happens is, let's take a simple parameter of size 4K cross 12K, which is represented in FP16. The overall size of this parameter on the disk is going to be about 96 MB. And we call it as the quantization schema out here. We call it as a group quantization. Yeah, there are various different quantizations MLC supports, and one of that is Q4F16.0. What it technically means is you have your source parameter in FP16, and I'm gonna quantize that into an int4 in a symmetric way. And these int4s are being packed into a storage element of 32-bit. So this 32-bit storage element is going to hold 8 of those int4s. And when we are doing this small localized quantization, the group size that we take is 32 elements. So that's what the specification of this group quantization defines. So what happens when we are doing this is yeah, we have the parameters in 4K across around 12K. And then what happens is we essentially go through the process of taking small chunks of 32 and then finding a scale for it and then quantizing each value into a 4-bit value. So finally it realizes into two tensors for us, two parameters. So one is the quantized parameter. Obviously, as you are converting from 16-bit to 4-bit, you will have one fourth of it. Yeah, you will have one fourth of it. So technically, your 4096 FP16 values will become 512 of UN32. And every group has a scale because you need that for again doing a dequantization on the target. So the scale will be stored in another parameter for us. So in this way, the original parameter will be converted into two smaller parameters. One is the quantized value, which is like 24 MB on the disk, and then 3 MB of smaller scale parameter. So that's that way we can actually convert this 12 GB of parameters into a 3.5 GB on the disk, and yeah, now we can 3.5 GB on a mobile device is having about 16 GB or 12 GB of RAM. It's okay. Oh, it's a good decent for given the if there is a strong requirement that we wanted to someone wanted to enable this model on the target device. And coming to the dequantization, so you might have a question like, how do we deal with dequantization? Are we going to dequantize this and then keep it and then the model will start using? The MLC will use it in slightly a different way. They don't dequantize and then again keep it as a parameter on the RAM. Rather, they do an inline dequantization. In this case, what happens is the inner loop is being dealt as as a single group. So when you are processing, we try to process that whole of 32-bit parameters. Sorry, the 32 parameters as a single group. So we read the scale and then we read the parameters and then we inline dequantize and then try to consume it while we are doing the math. So we might when you look into the pressure that we are going to have on the compute power with respect to the this inline dequantization, um, it realizes into every EU in 32 packs 8 values in this. So when we look at the amount of effort that the instructions that will go into this dequantization and all that, it's about 8 shift and mask instructions followed by it converting from int4 to fe16 and then the fe16 additions on top of it. So it's about one instruction versus three instructions, and then which doesn't look like a pretty significant pressure on the Adreno GPU for us. And then yeah, we were good on this part. So coming to the various optimizations that we have done with respect to enabling these models on Adreno GPU with OpenCL target. When we decompose these, yeah, before that probably, yeah, when you look at these workloads, right, there are two models in this. There is two sub models in this. Basically, there is one is on the decode and then another is on the encode. The encode is all about when user enters a prompt, how we will process that and then converts that into a kind of a state information, and then the decode will come into picture, consume the state information or the and the user prompt related data, and then it will start emitting the response for you. Like for example, if we say write a poem about moon or something, write a poem about the moon is your input prompt. So the encode process will try to analyze that and then convert into kind of a context, and then you have the decode process which really starts emitting the output for you in terms of a small poem about a moon. So the optimization out here is all about how do you make these encode and decode sub functions or sub models perform efficient on the target. So when we so in that process when we profile this decode, we have got about all these various different kernels, and then there are top 4 or 5 kernels marked out here are significantly taking the processing power. I mean, they are actually pushing the maximum amount of time. So our focus was about optimizing these layers, and is our overall agenda. And yeah, I'll show you the optimizations in the next slide. So looking at the numbers, the kind of a progress we made, when we had taken the baseline numbers, there are like 5 to 6 tokens on our Snapdragon 8 Gen 2 and Gen 3, and then all the optimizations that we have brought in has were able to improve it by nearly some two to around 2x for both the devices. So the optimizations are there all across the board. So when we initially looked into the kind of a code that is being generated and then profile it on our hardware, we saw that the concurrency that is being used by these kernels is pretty low, and the vectorization and overall we see a significant amount of gap in terms of utilizing the resources that we have it on the Adreno GPUs. So we modified these schedules for all these top layers, and improvised a few of these things in terms of getting a better correlation, and then load store throughput and all that. And these top layers with all the low hanging fruit, we are able to push up the performance overall by 35%. Then we looked into the architecture side. What is it that more we can do? So we saw there are quite a few transpose ops that are there, and then technically, and I don't know, we don't need to transpose and then do a matmul. Rather, we can keep the original data and then slightly work around the schedules to consume that data without transpose, and then we could get through it. So introduce a couple of passes in the MLC and TVM workflow to take out those transposes, and then enhance the schedules to according to the new tensor shapes we have received. So that gives a further more uplifting on the performance. And then there are quite a few low-hanging fruits all around. Like we used the pre-compiled binaries for loading OpenCL kernels, and then few kernels we promoted to the texture from the fact that Adreno does better job with textures than buffers, and then um, some initial warm up, and yeah, these are a few low-hanging fruits. And then coming to the on the target, when it comes to the edge devices, I talked about the power and all that, right? So there is some things which we have done with respect to few experiments we have done to see how does the power consumption of the target device. The decode operations for us is mostly a 1D to 2D multiplication. So by nature, all these decode layers are bound to the memory. So we don't need to actually run the GPU at the higher clock to look for better performance. So we try to lower the GPU clock a little, and then we're able to find a sweet spot where you get a better efficiency, where the decodes performance still sustain even at the little lower clocks of the GPU. So in that way, yeah, we can really get a good performance per watt on Adreno GPU for this model. And coming to the encode section or the prompt processing section, these are the various tokens, various different layers that we have out here, and then similar to the decode optimizations here, also we identified the top kernels, and we try to do an optimization. And yeah, on the decode side, we have got pretty significant amount of push, primarily driven by our hardware understanding of ALUs, and then there are significant amount of proprietary work that went into it. So when we look at the nature of these kernels on the decode side and on the encode side, these are all like ND to 2D multiplication. So these, and by nature, these are all ALU bound. So we have done some amount of handcrafting these a few of these OpenCL kernels to really push the encode performance out here. And the approach we are taking to make these things available is through the BYOC. BYOC is our earlier way of the existing way that we had already within TVM community for pushing the proprietary layers to make them available for the larger audience. So that's about our progress with respect to the enabling LLMs on Adreno GPU, and these are the kind of performance improvement that we could get all around. So what is it that we are going to have in near future? Right now, today the MLC supports very wider range of networks, and then we are focused to improve all these all these models. And we'll be making we are already made some of our enhancements available in the MLC community, and then we are committed to keep up with the community progress and then make Adreno enhancements doesn't break, and they'll be functional, and then they'll be giving good performance uplifts into the in the MLC community. And right now, in the near future, like similar to Llama, we are right now focusing on Mistral and Quen and then Gamma and all these models. Basically, they are all functionally up and running on Adreno targets by using MLC. But yeah, there is a significant amount of performance gap with respect to what we could really achieve on Adreno versus what is there right now. Yeah, that's all from me today. Yeah, thank you very much.